this video, we're going to do a problem from 2.6 using Euler's method. We're going to do problem number 4. If you want to follow along with what I'm doing, this is the example that is given to you in section 9.1, that they start off with a comparison of two different forms of Euler's method. We're going to do the original form from 2.6. We'll come back and do another method, an improved method in our next video, which is what they teach in 9.1. But I'm going to go ahead and write the problem out for you here from number 4 from section 2.6, and it says use Euler's method to approximate the value of y at x is 1.5 for the solution of the initial value problem y prime, which we're going to call f of xy for this problem, is equal to 2xy, and y of 1 equals 1, which means x0 equals 1, y0 equals 1. Is what that initial value problem tells me, that those are my initial conditions for x and y. And so I'm going to find what the exact solution of this would be using my techniques that we already learned in chapter 2. This is a separable differential equation. So I'm going to have 1 over y dy is equal to 2x dx. ln of the absolute value of y is equal to x squared plus c. And that means that y is equal to e to the x squared plus c, or some constant c times e to the x squared. And we're told that when x is 1, y is 1. So 1 equals c1 e to the first. So e to the negative first is equal to c1. That means y equals e to the negative first times e to the x squared. And that means that y equals e to the x squared minus 1 is our actual solution to this initial value problem here. So if we wanted to find out exactly what y of 1.5 was, we would need to calculate e to the 1.5 squared minus 1. We're going to use Euler's method to approximate that. And I'm going to use Excel to help me with the calculations. You may want to use a calculator, but I just want to show you in spreadsheet form and show you that there's some automation that Excel can do that would be helpful to you with formulas. So let's go ahead and I'll share that now. There we go. So what I'm going to do is we're going to start with an h value at delta x of 0.1 is what the problem started with. So I want to start with 1 and then 1.1, and I just want to get this down here, 1.2, 3, 4, 5. so that we have all of our x values. Our y values start at 1, and then we'll calculate the next value here as our old y value plus our 0.1 times, and then this is where our f of xy comes in, 2 times x times y. And then that gives me 1.2. I'm going to drag and drop that formula all the way down, and it calculates all of those for me. Now I'm going to calculate my actual y value, which is going to be exp is the exponential function done there of, and then my exponent is going to be x squared minus 1. And let's drag and drop those like that. That looks good. While we're at it, let's go ahead and find my my absolute error in these values so that you can see how close we were, and the closer we are to the given value, the better our estimate is going to be. So we can see that by the time that we're down here to 1.5, where we wanted, we're off by 0.5625. Let's change that to a percent error by saying that this is equal to this number divided by this number here. So that's the absolute error divided by the actual y value here. And I've already set it up for this column to be percents. So we end up with a 16.12% error. If we have a delta x or an h of 0.1, which is fairly large, right? But we want to go back and do the problem again now with more steps, and hold all this information in your head, write it all down. I'll actually come back and just do a separate table here for it, that we're going to want to start with 1 and 1 again. And then we want our delta x this time to be 0.05. So 1.05. And we're going to take 10 steps this time to get to 1.5. So 1.1, 1.15. And you can see the automation going on right there, that takes me to 1.5. Similar process here is I'm going to say old y value plus, and now it's 0.05 times 2 times x value times old y value, like so. And we're going to take that and run it on down here, and good. And we've still got the same function here. So this is going to be, actually, I don't need it there, but I'll put it there anyways, equals exp of 1 squared minus 1 . There we go. And I want that here. There we go. And this one is, again, just a perfect 1 there. And let's go ahead and find my error. That this is this column minus this column. That all looks good to me. And then percent error is this column divided by this column. Run this on down, and we're going to change this to a percent. And let's run this out to a couple more decimal places there. So there we go. Now, you can see that by taking more steps here, that you increase the accuracy significantly of your estimate, where my estimate here for y of 1.5 was 2.927813. The actual value was 3.40343. Here we got to an approximated value of 3.173277, and the actual value was 3.40343 again. So we're within 9%. That's still not great. It's better than nothing, right? But exponential functions change direction very quickly. So using a line, this is a linearization technique, is not necessarily a good way to approximate an exponential function like this. So this is maybe the best that you can do, though, is to use this tangent line linearization technique to help you out with this. But we're going to improve this method for section 9.1 and see if we can get that absolute error and percent error way down and get a much better estimation of things that are close to our given value. So 1.5 is close, but not really that close. Relatively speaking, with calculus, we would be much happier if we were talking about something like 1.1 or 1.01 if we were looking at a initial value of 1 than something that was 1.5. So anyways, that's it for this video. I'll come back next time to talk about the improved function, and I'll leave this data up here for us to compare to our new method, and you'll see the improvement. So I'll leave these same h values or delta x values of 0.1 and then 0.05, and we'll compare the two values here next time. See you for the next video.